Good afternoon, everyone. Hi, I'm Debdev. We have with us today on the Liverpool Virtual Seminar Series on Data Science, Dr. Sofia Vallecorsa. She's a researcher in the fields of scientific computing, machine learning, and quantum computing with application in high energy physics at CERN. She's the coordinator at CERN Quantum Technology Initiative, while her main research focus is in the intersection between AI and quantum computing. So yeah, Sophia, the stage is yours. Please go ahead.
Thank you. So I assume you can see my slides. Okay. Another point I wanted to make before starting is please do ask question at any point. You could raise your hand. If I don't see, I mean, I will try to keep an eye on it, but if I don't see it, just shout, basically, as much as you can do that over Teams. And last thing, this is a talk about quantum computing application. It's a perspective that we have at CERN, and that is driving the research that we're developing here at CERN. But I assume that your expertise is mostly at the level of data science, artificial intelligence, machine learning. So throughout the talk, you will hear me talking and using language that is related to that. Okay, so if you find that instead I say something that is not easy to understand, again, please let me know. Okay. And with that, I'm very, very happy to be here and to talk to you about the activities that we have in at the CERN, within the CERN Quantum Technology Initiative, CERN QTI. And since I'm typically late, I will start already now with the lessons learned. I want to share with you. Quantum computing is a very, very interesting technology. Unfortunately, it's also a technology around which there is a lot of hype that is built. And so doing research in these conditions really, really means to try to fix a few important points. And for me, the most important are the ones that I listed here. This is certainly not a plug and play technology. And at this stage, there are a lot of different solutions that are being considered for building quantum computers. So in CERN QTI, we are still agnostic. We are happy to experiment with all of that. This is my personal point of view. What I think is that longer term, we will not end up with a single technology that will replace all, and that will be suitable to all problems, let's say. But there will always be a case for developing specific hardware for some specific problems. And I'm happy to discuss more of this later on. The other thing is that we want to manage expectations. So it is really, really important that we look at the technology from an incremental integration point of view. So on the one hand, we want to start with R&D. And as I wrote there, test the technology in realistic settings. But this is also something that needs to take into account how we could, stage by stage, make the technology more usable and integrated with our computing models, the way we are able to, or we are used to working at this stage. Okay, so if we do that, then we are naturally building something, an approach that will allow us to integrate the new technology more or less seamlessly. And I want to stress quote unquote around the seamlessly word here when it becomes available. That's it. So why are we looking into this at CERN? I do not have an introduction about CERN. I don't think it's needed. But again, if you want to know more, please do ask questions. What I want to stress is that CERN, as one of the major experimental physics labs in the world, has a very diverse physics program. Obviously, collider physiks with the Large Hadron Collider and its upgrade is a central interest, but there are a lot of other activities that are ongoing, in particular, a series of fixed target experiments that profit for the general accelerator infrastructure that we have, but also studies on nuclear physics, research in the field of antimatter, neutrinos, but also obviously contributions to the theoretical domain. And together with that, or attached to that, there is a large range of technologies. So an important also technology R&D program in the different areas that you see here. So anything that's related to the development of future accelerator, future detectors, but also the area of scientific computing. You might know that the CERN community, the high energy physics community more in general, has been working for many, many years using a distributed approach, so a distributed infrastructure, the LHC computing grid. And this has shaped, in some sense, the way we think about the computational problems in our domain, okay, and algorithms. And so, sorry, just move fast. And so there is a certain evolution that is going on also at the level of scientific computing. Now, if you think about these three main areas and you think about how the different technologies, quantum technologies, are typically categorized, then you would see that everything that has to do with quantum computing and simulation is very well matched to our interest in an evolution to scientific computing, together with the discussions about networks and quantum communications, while sensing as an area is closer to what's happening, the activities that are happening at CERN in the area of accelerators and detectors, research and development. So I am not here to talk to you about an introduction on quantum computing, but I just wanted to give you a very basic few concepts that maybe will allow you to, if you're not already familiar with it, and I mean, the ones that are, please bear with me for a few minutes. But I want to bring everyone at the same level from a very specific point of view that I will use to discuss quantum computing today. So, and this point of view is a computer scientist perspective. I'm not looking at this problem as a physicist. That's my background. But what I want you to think about is how we actually translate in very, very practical terms from a computer scientist point of view, the principle of quantum mechanics as a way to enhance computations, okay? So if you think about the concept of state superpositions for quantum states, then this naturally translates into the possibility of an exponential speedup. So is it the speedup that we can actually leverage in our algorithms? This is the first and probably one of the most important questions. And other fundamental concept of quantum mechanics is and property of quantum systems is the entanglement. Entanglement as a way of encoding very, very complex correlations that can lead also to the ability to represent functions that in fact would be intractable classically. So is this something that we can properly leverage and maintain in the way we implement algorithms on quantum computers? So those are probably the two most discussed, or the let's say the most well-known properties and their corresponding implications. But there's much, much more. If you think about the fact that typically the gates, so the operations that can run on quantum states, those are unitary transformations, therefore naturally reversible. Does this automatically lead to a concept of reversible computing? Actually, we will see that this is almost, it's a very, very difficult point to make, because there is a measurement step in order to evaluate the output of one of our algorithms. What we need to do is to measure a quantum state. This is something that will give us a result with a certain probability distribution according to the Born rule. We are actually in the domain and in the realm of stochastic computing somehow. And there are other interesting features. How, for example, the concept of non-cloning, the theorem, the non-cloning theorem for quantum states, how does it relate? So the fact that you cannot just fully copy the state of a quantum state without losing information or disrupting in some way the information, depending on the protocols. But so does this have an implication on information security? And what about everything else that is related to reproducibility also, and coherence and stability of the results? So if you take this lens, let's say, then it becomes very, very interesting matching between or let's say, if you take this length, then you have a certain number of instruments that allow you to evaluate the performance of your algorithm in a way that it's really powerful, I believe. Okay, so again, few minutes. What do I mean to implement a quantum algorithm on quantum states? You have a sketch here that highlights on the very left of the slides how you would initialize a certain number of quantum states. Here, each one of the zeros would represent the initial state of one qubit that go that are in this specific case would be all initialized in a combination of zeros. And this general picture shows you how you would build an arbitrary quantum circuit as an algorithm. So you would need to start from your quantum states, initialize to some value. Then you would need to embed the classical data. I'm assuming that this is an example in which we want to process some classical data on quantum algorithm. This is actually a specific case. That's not all you want to do with quantum algorithms, but let's take one of the most complex. So we have classical data. We want to process it through a quantum algorithm. We need to, first of all, load it on our quantum state or embed it, as it is usually say. It means that we need to transform the original quantum states, applying some transformation that takes into account the classical input. Okay, so that encodes the classical input in the quantum state. Then you would run a certain combination of operations, so those unitary gates, those unitary transformations that would also apply to single qubits. So you can imagine that throughout the algorithm, one line represents one qubit, and when you have squares that go across, you are actually entangling. So you are combining using operations that apply to multiple qubits. Some of those operations can be parameterized, and you will see why I'm stressing this at this stage. And the last step is the measurement step. It's the moment at which you actually extract the output of your algorithm. And what you actually extract is a distribution on a series of observation on your states. Okay, this is the important part that I was saying before. That has a major impact on the way algorithms, on the way you can actually characterize the properties I mentioned before, and in particular, the possibility to leverage this exponential parallelism or the reversibility of an approach. So that said, so those were my just 3 minutes or 5 minutes on how you actually build a quantum algorithm. So very, very high level, but it's obviously a simplification. This is a technology that has been around for quite some time, with a lot of with a few very, very well-known algorithms that are known for many years, and many others that are less, I would say, for which clear advantage is not theoretically ensured, but that have proven very useful over time, and you'll see. And why do I stress this? Is because most of these current approaches are actually hybrid approaches that introduce quantum computers as accelerators. So basically, in the same way you would think about heterogeneous architectures today that enhance the capabilities, for example, of HPC center, you could think that in a very near future, you would have HPC centers that include also access to quantum computers. And this is something that is already happening, actually. You see what you see on the sketch is a list of HPC centers within the Euro HPC joint undertaking at the level of the EU that are planning to install different technologies, quantum computers in their infrastructure. Okay. What's interesting is that this is also not just at the level of hardware infrastructure. There is a lot of work that is already ongoing in defining how to best actually deploy algorithms on such an infrastructure. Okay, it's not just a matter of defining a problem, defining the algorithm that can solve it, the approach to it. There is a whole, range of intermediate steps that are needed in order to actually run it. And this is something that for classical computing we almost forget about, but it's still very, very important and needs to be designed, and it's at this stage being optimized in the quantum or hybrid domain. And the other thing I wanted to mention, and if you want, I mean, I don't have it here. I have it in the backup slides. I can show it to you if you're interested. But the general idea is that within the early 2030s, a few major companies, I would say, that are at the moment technology providers for quantum computers are promising roadmaps that will give us access to hardware that is in the fault tolerant, or let's say pre-fault tolerance domain. It means that we will have access to hardware that will have logical qubits. So this concept of already corrected qubits, which do not suffer from the problem of noise and decoherence, because those are actually just logical concepts that combine many physical qubits together to correct automatically for that kind of behaviors. And the possibility to run between the thousands and the millions of gates, which will actually give us quite a powerful, I would say, quite a change in the performance that we are able to test today. But obviously, the question is whether we do have applications that are suitable for this, running on this domain. Now, when people talk about quantum computing and fault-tolerant quantum computing in particular, the first problems or the first applications that come to mind are related to cryptography and security. I want to tell you right away, I will not talk about that. That is not part of the research that we do at CERN. We do not have that kind of expertise, and we do not need that kind of, it's not among our objectives, okay? The applications that we study are really related to what's important for us at CERN and connect somehow to the points that I made before at the beginning of the presentation. And this is exemplified. This is just one single slide that I have on how our Quantum Technology Initiative is organized at CERN. The idea is, this was launched a few years ago now, in 2020, to organize applied research on quantum technologies. And it has this double, I would say, side. It's a double-sided initiative in the sense that it has two main objectives. At first is to understand whether we can use quantum technologies within our research plan or program, if it's something that different ways can enhance our capabilities. But also the other side of this is whether anything among the very broad range of technologies that CERN develops for its own need is something that can contribute to research in the quantum domain. Okay, so this is really this double focus that is extremely important for our initiative. And from the scientific point of view, we are organized across four centers of competence, three scientific areas, actually. One is about hybrid quantum computing. This is what, everything that I will talk about sits. Then there is the part about sensing, which we call the CERN Quantum Technology Platforms. That's really mostly focusing on, well, I'll tell you more, just one slide, but really focusing on material and sensor technology that's developed at CERN. And quantum networks and communications, again, this area focuses more on the aspect of distributed, so networking, so for distributed applications, either networks of computing, so distributed computing, or sensors. Not so much on the aspect of secure communication. You might be familiar with the QKD, the quantum key distributions protocols. We do test those, but they are not our main focus for research. And another very, very important aspect is the aspect of collaboration. And we have what we call a QTI Hub, which is basically a collaboration framework that is specifically designed to set up research project, joint research project with either academic partners or industry, academia partners or industry. So let's focus on quantum computing. Okay, we want to understand to which extent we will be able to integrate quantum computing or quantum computers or this new paradigm within high energy, the high energy physics computing model, and what are the challenges related to it. So naturally, we started working in the realm of near-term quantum infrastructure. So the idea of those accelerators with limited capabilities that are integrated into broader classical systems. That is also obviously we are also preparing towards studying. We're also studying how our approaches, our algorithms will scale in the area of fault tolerance. Okay, so this, as I said, is also something that's coming very close, because if we find that there is performance limitation to some solution that we have set up and tested today, then we want to understand whether this is something that can just simply go away when we will have access to fault tolerance, or whether there are additional intrinsic limitations that make that algorithm or that approach unsuitable to our problems. So this is done by looking into, first of all, what are the most promising applications in high energy physics, what are the aspects related to the usability of this approach, but also what is the theoretical characterization of those algorithms, the behavior of these algorithms, in particular scaling up. And I also want to stress that most of the developments that we have are actually common to areas beyond high energy physics. So this is something, most of the results that we present can actually be reused. So what does useful mean for us in this context? You see here two examples of the work that I will show you later on. So I'll give you more details about this. But the idea for us is that we define quantum, well, not we define quantum advantage, but let's say we are less interested in the proof of a quantum advantage per se. So of finding a problem that we can solve, well, also through the years, the concept of quantum advantage has changed over time. So we shouldn't go in that direction. We can discuss it if you want. But let's say for us, what we are interested in is improving usabilities of the systems in realistic problem. And this can mean, for example, having an advantage in terms of saving resources that are needed to solve a problem, even if we have a classical solution to that same problem already, or improving the general performance of a tool. And you see two examples here. One is about resource efficiency. This is the example about the quantum reinforcement learning example I'll give you in a few slides. And the other one is instead a case in which we can improve the capability of our tool by implementing in this specific problem of a specific anomaly detection problem in a quantum setting. So let me go now. Is there any questions so far? I don't know if I'm allowed to take them. If there is anything, I don't see any raised hand.
Yeah, at the moment there is nothing on the Q&A chat. So yeah, please go ahead.
Okay, so I have selected. I will discuss with you our work on quantum machine learning algorithms. I think those are very, very interesting and broad class of actually algorithms. So I'm happy to also have a point of view of someone that is expert from the classical perspective. What do I mean when I say quantum machine learning? There are actually also in this case different kinds of different interpretations, different ways of using quantum and machine learning, meaning trainable systems, data-driven trainable systems together. What we mean by that is that we want to use quantum computers to improve those trainable data-driven algorithms, okay? And so what we are doing is basically testing what happens to a data-driven approach when we implement the trainable algorithm on a quantum computer. This is what we mean by quantum machine learning, the way, what we mean by quantum machine learning. Please note that there are other fields that are very, very active. For example, the other way around, how you actually can use machine learning, classical machine learning algorithms to improve quantum technologies. That's not the how can I say, the topic of this of my talk today. Okay, so in this context, so if you work on this kind of tools, you can recognize the typical simplified also life cycle for this kind of systems. This is the exact same life cycle that you implement in a quantum domain. And if you do that, obviously, then you can start thinking of quantum advantage in terms of representational power, for example. So whether your trainable system implemented on a quantum computer can learn more complex distribution than what you can actually do classically. Whether there is a speed up and you know, in the either in the training process or the general speed up in the algorithm itself. Whether there is an advantage in terms of reduced computational needs and reduced sample, reduced data set size and so on and so forth. So you can imagine that if that is the kind of problem and algorithms that you're studying, then the definition of advantage becomes very broad. I can tell you right away that there are there are many, but there are two main major challenges for the application of the development of this kind of algorithms and the application to realistic settings. And those are related mostly to the point of classical data loading on quantum states. So that initial step that I highlighted in the first very small circuits sketch. And I highlighted in bold here the trainability of quantum systems, of those quantum systems. This is for people that have a classical machine learning background. This is a very, very interesting topic that allows you to study basically what happened to your optimization process and to your model once that is defined within Hilbert space. So I will explain to you these two, well, not really explain, but give you a glimpse of what it actually means to try to address those kind of problems. The first is the point of classical data encoding on quantum states. There are many, many different approaches that have been taken to load, so to encode the classical data on quantum states. You can see a few of them listed there. They all have their pros and cons. And now the important point is that if you recall the initial little sketch, what I showed to you was basically a single layer of operation that would be used to encode classical data on quantum states. What actually happened is that was a very simplified view, because what actually happens is that you might actually need a very, very deep, a very large number of operations in order to encode your data. And so the choice of the encoding is always a compromise between trying to use a representation that is as compact as possible, because what you really want to leverage is this exponential parallelism I mentioned before. You probably heard many times discussed it as if you want to, if you have access to n qubits, it means that you are able to store 2 to the n classical bits. So exponential advantage. This is what typically is called amplitude encoding. If you want to do that, then it means that you can see here that it means that you need to have a very, very large number of operations that in order to set it up. And at this stage, so for most of the hardware that is available today, this is the limitation, okay? It's actually broader problem than for quantum machine learning. This is a general issue that is affecting most of the quantum algorithms that run on classical data. I chose here two examples to show you this. The first one to the left, the quantum associative memory, I believe it's one of the very, very first quantum computing papers that show the quantum computing applications for high energy physics. Sorry, quantum computing applied to high energy physics problem. And this was the problem of reconstructing particle trajectories from detector hits. And so the authors went to try and measure how many information units, so how many quantum versus classical bit would be needed to set up to implement an algorithm of associative memory. And they could obviously see exponential compression, so advantage from the point of view of the number of memory units needed, but they had to rely on a few example algorithms that actually gave a scaling in terms of number of operations that was unfeasible to be applied at large scale. On the right, you see something similar. This is a result that we have recently published that's very, very recent. And it does something, again, very, very similar, evaluating what would be the number of operation of gates that are needed in theory, but also optimized to a specific quantum technology, in this case, superconducting qubits, to set up a prototype of quantum databases. Okay, so here, what I want to say is, yes, it's true, you can leverage exponential compression using a quantum state instead of a classical memory, but you are going to pay the price in terms of operation. So you need a system that is stable enough to actually run all of these large number of operations. Now, if we go back to the concept of quantum machine learning models, so when you typically think about a problem like this, you study your data set and you need to choose the kind of models that you want to train. And this is also true in the quantum domain. There are three main approaches, actually 2 + 1, I would say. One is the analog of the neural networks approach, classical neural networks. The second is the analog of the classical kernel-based machine learning, which not sure how many of you recall. Those are very classically, from the classical perspective, those are very, very interesting models, rather simple. Let me start from the neural network algorithms. This is what we typically call variational algorithms, because what you see a behavior that's described here by this sketch. And it's very similar to, again, the way neural networks work. This is a reimagining of the initial sketch that I showed you at the beginning of the talk. You would have your input quantum state that is initialized to some value. Then you have the feature map, so this stage at which you load classical data on your quantum states. Then you set up a certain number of a circuit, so a certain combination of parametric gates. Then you run your circuit, you run your measurement, you build a classical loss, and you build the classical optimizer to optimize gradient-based, for example, the parameters of your quantum circuit. And you repeat the iteration data point by data point in order to train it the same way you would classical neural networks. Okay, so there is really almost a one-to-one connection between the two concepts. The kernel-based method is very interesting from the quantum perspective because it leverages. So basically, it's almost like a native implementation. You interpret the encoding step, so the encoding that you need to load your classical data on the quantum step is interpreted as a feature in a kernel method. So you can build your kernel by just inputting your classical data on the quantum state. And then once you've done that, then you can leverage all the nice properties of kernel methods that give rise, for example, to convex loss functions and so on and so forth. And so then that part of the algorithm can work also in the quantum domain. I will show you. There is a third approach that has been a little bit less investigated, is a little bit less popular, I would say, just in terms of number of publications, recent publications Probably. This is everything that is related to implementing in quantum computers the same concept of energy-based machine learning. So you define you define an Hamiltonian, an energy function that represents your problem, and then you try to find, and it's data dependent, obviously, and then you optimize it by minimizing this energy function. Okay, so the typical example is the Boltzmann, is the various family of Boltzmann machines. So maybe I will skip this. No, maybe not. Just to stress a little bit more. If you wanted to take the variational approach to implement a quantum classifiers, classically you would have a neural network that defines basically the mapping between your input and your output, so the labels, your input X, the certain number, the set of parameters, and your output. And in the quantum domain, basically you'd be doing the exact same thing. Your circuit, so your combination of gates that are dependent on your input variables and the certain number of parameters are run, and the measurement that the observable that you measure on the output state is what you can map to your to the label. So then you can proceed with the optimization the same way you would classically. And if you're curious, I don't want to spend time on this, but I'm putting this few slides for reference here. If you're curious about you actually do this in practice, you have what is called the parameter shift rule, which is basically a way of calculating gradients on quantum computers. And it's in some sense a very, very close to the idea of finite derivatives, or the classical finite difference rules as best defined, in which that consists in evaluating your circuit using of shifting with a very, very small amount your theta parameters, so your trainable parameters, and using those differences to approximate your gradients. You can imagine that this can become a very, very expensive approach. And similarly, again, don't want to spend time, but I leave it for reference. If you want to go further into this direction of the gradient approximation, another approach, again, this exists well beyond quantum computing, but it's popular for training quantum machine learning algorithms, is the SPSA methodology, in which instead of trying to calculate the different gradients step by step in your optimization process, what you do is you sample small perturbations around the central values. And by doing that, what you can do is to move around the optimization space. What happens? So when you do this, again, methodologies are very similar to what you would do classically. When you implement those in the quantum domain, then you run in a certain number of problems. Some of those are common to classical networks, but appear in a slightly more different fashion. The problem of barren plateaus is one of the most best known. What happens is that when you set up a variational algorithms and a gradient-based optimization, what you're going to see, unless you're careful, and there are techniques to try and reduce this effect, you will see that your gradients will decay exponentially with the number of qubits. This was observed very early on. If you look at the dates, this is an archive from 2018 that was published by the Google team. Then this is true. This has been observed in many, many different setups. And so, and it's particularly, so again, the problem becomes harder when you increase the size of your network. So increase the number of qubits. This means that whenever you build a model in this field, what you need to do is to try to compromise between the expressivity of this model. So how complex is going to be the range of function that your model can learn with respect to the trainability of the model itself. So how likely you are to actually converge. Now, again, and a well-known problem actually made worse by the fact that decoherence, so the existence of quantum noise and errors is something that can have an impact, can also exacerbate, also make this problem worse by generating barren plateaus. But there are a certain number of directions that can be taken in order to avoid this problem or minimize it. In particular, setting up gradient-free optimization, choosing your loss functions or the models, the topology of your quantum circuit, variational circuit property, or trying to go towards kernel-based models. If we use kernels, however, I feel like I'm giving you hopes and then shutting them down. You will see that this is actually not true, because we do have things that we can do with quantum machine learning. But let me also point out again, kernel methods are very interesting, and they are a solution to the problem of barren plateaus to some extent. However, they have their own problems. In particular, remember, kernel methods in this domain are built by basically mapping, so designing the feature map, so the quantum circuit that maps the classical data to the quantum state. What you do is, so those become your feature maps in the exact classical jargon. And then if you build what's called the fidelity kernel, so you build the fidelity between the two states, you can see the X and Z parts of the circuits that are combined together in the sketch. Then that becomes your kernel, and then you can train it classically. Now, the problem with this approach is that you could feel the, I mean, let me rephrase. Logically, you would try to use at best the Hilbert space, the possibility to having access to a very, very broad multidimensional space. This has the risk of resulting in a very, very sparse representation of the data that will make more difficult convergence and will limit the predictive power of your algorithms. Okay, so yes, kernel methods are an alternative, but they also need to be treated with care. In fact, there is work that we have done. We are not the only one, but we've demonstrated its applicability to a binary classification problem in high energy physics. One of the solutions to this is to use kernel methods for trainability, but project them on a lower dimensional space, so that you're actually not using the full Hilbert space, but you are restricting your kernel on a lower, in terms of locality. And this has been proven to work better. Let me stress again that there is a lot of classical machine learning that is coming in here, because the concept of projected kernels is actually something that is born in the classical domain. Okay, so theoretically we have, we do have a lot of options to choose from. We have interesting models that we can test. There are pros and cons. There are problems that need to be studied. Overall, it's a very interesting and I can tell you challenging field. As far as the community is concerned, it's not also even entirely sure that this will be among the first algorithms that will be run on fault-tolerant hardware, because of the problem related to data challenge, to those two problems that I mentioned to you, so trainability and data embedding. But what is it that we can do with those? Because I talked a lot in general, I wanted to give you a couple of examples of what you can actually do with these models. So I will go back to the two original performance plot that I showed you before. And I will start by describing to you the example about anomaly detection. This is more of a motivational slide. Why is it interesting for us? Well, because there is a lot of reasons. We know a lot already about standard model and of particle physics, but we need to understand better what lies beyond. And since we either choose a specific theory model for what lies beyond, or we need to take an anomaly detection kind of approach. And you know that you probably know that machine learning algorithms can give you very, very good anomaly detection tool. because you can take a completely unsupervised approach that will allow you to train on the physics, in this case, the standard model physics that we know very well, and will flag any difference with respect to it as an anomaly for further study. So this is the approach that we take. And it's in this context that we built, we used our quantum anomaly detection tool. Why am I using this example? This is a fairly also old example for us. This was published now a couple of years ago. Why am I using it? Because I think it's very nice, very good to explain how these tools are actually used in practice today. Have a look at what's on the left side of the slide. The sketch shows you that this is actually a so this is a hybrid implementation in which the role of the classical part is very, very important. The way you use those algorithms today, in order to go beyond to these problems I mentioned about the possibility of doing classical data embedding of quantum states, is to use a classical autoencoder as a compression step that takes your original classical data, brings it into a latent representation that is small enough that at this stage we can load it on a quantum computer, and then we load it on a quantum computer and we run our quantum anomaly detection tool. This is an example, but it is the way, I would say 95% of the quantum machine learning algorithms are run today on real data, or let's say on realistic data sets. If you do that, what you can actually, we can discuss more in details if you have questions, but basically what we observe if we measure the performance of the tool with respect to classical tools is that, well, we can do better if we compare to classical support vector machine, which are by no means the state of the art in terms of anomaly detections today. But what's most interesting in this plot is the fact that we can actually recognize that there is a role that the entanglement, the quantum entanglement across qubits is actually playing an important role in defining the performance of these systems. This was for us the major result that we wanted to take out of this study. The second example I have, by the way, I didn't ask how long I have for this seminar. This is 1 hour, right?
Yeah, Sophia. So ideally, we generally try to be with the question and answer 1 hour, 5 minutes. So maybe okay. Like so few minutes if you yeah.
Okay. Few minutes. Let me show you this and then I will close. So I wanted to show you the second example because this is a very different approach. This is the idea of using quantum annealing to train reinforcement learning agents in the context of optimization of a particle accelerator. So there are different beamlines at CERN. One of them is the awake beamline. It's an experimental beamline that's studying some specific electrons technology. Well, that's not the point at this stage. We use it as a typical beam steering setup in which we would have particles that go through a series of magnets that squeeze them around some nominal direction, some nominal trajectory, and then we would have a certain number of monitors that will study their effective position. And so the point here is it's a multidimensional problem in which we need to optimize the trajectory. So we need to optimize the choice and the deflection that each one of the magnets is inducing in order to steer to the optimal spot the particle beam. And so this is, I mean, per se, using classical reinforcement learning for accelerators tuning is not new. That has been proposed already in the past. What we wanted to see was whether we could actually improve this with a hybrid setup, and we can. This is the result of this plot. What we showed is that we could actually train a much smaller network in a fraction of the number of steps that are needed to reach optimality if we used an annealer with respect to a standard classical optimization. And the plot here on the left in particular shows you a comparison with, so this is now no longer, I would say, a toy reinforcement learning agent, but we actually took the made the effort to run a certain number of configurations and scan for optimal classical solutions we could compare to. And you can still see, I don't know if you can read the logarithmic scale, that we could actually do this in a way that is much, much more efficient. And what I find most interesting about this work is that for those of you who are familiar with the technique, this is actually a hybrid actor-critic algorithm. It means that we have an actor that is classic, and the one that is performing the action, and the critic that is used only at training time, that is quantum. So our implementation allowed us to speed up the training through the quantum critic, but deploy the classical actor actually on the classical hardware GPUs that we have at CERN. So I'd rather leave some time for questions, because this is, I think I have only, yeah, what I wanted to say is basically this. Heuristic results are not necessarily enough. So for us, those are heuristic results. They're not enough. They need to go hand in hand with actual characterization of theoretical characterization of the algorithm, and this is actually what motivates us. The other bullet points that you saw me showing before, when I discussed the hybrid, the plan, or the research plan for our hybrid quantum computing center of competence in QTI. So there is a lot of that is going on. I can talk about that if you are interested. I have additional slides I can show you, but maybe it's better if we stop the discussion here now, so we can focus on this initial demonstrator. Thank you.
Thank you, Sofia, for this nice talk. Now the session is open for questions. So I would like to say to the audience that please feel free either to raise your hands or type into the question and answer chat box. I'll have a look. Meanwhile, till people write the questions, I've got a couple of questions I'll quickly ask. Yeah, just as a exponential memory compression side, like in realistic high energy physics over workflows, where do you see this this compression basically making the biggest difference? Is it the simulation, or the data analysis, or the real-time predictions?
Yeah, so there's no, where is it? So actually, this for me was a very nice example, this associative memory. I didn't explain what this methodology is actually, but this again, as the concept of associative memory comes from the classical domain. This has been used by many experiments, including Trigger at the Tevatron experiments many years ago, where you would build basically a database of possible patterns, detector hits patterns that could represent particle trajectories. So you would have this bank of predefined patterns, and then every time you take a picture, so every time you'd have a combination of a measurement of hits in your detector, you would compare to the different elements in this bank to find the one that would be closer, and that becomes your trajectory candidate. So this is a generic algorithm that has been proved to work classically for doing particle trajectory reconstruction. And this quantum implementation tackled the same problem and really tried to measure the advantage that we could expect in implementing that same, let's say, methodology, it's a similar methodology in a quantum domain. So for me, it's a very interesting example because of that. It started from a pattern recognition problem.
Nice, okay, thank you. My second question was, because you nicely explained with the limitation, the kernel-based methods and also the energy-based one. With my limited understanding, I was curious, is the energy-based model then would be better suited candidate here, because considering the high dimensionality of the data and the complex dependency, or that's like a long way to go, more we try the kernel based?
So it's a very good question. So energy-based models are great candidates. There is great potential. So in fact, they are among the models that we are currently more deeply surveying. In particular, we have work now that tries to evaluate and predict to which extent we can expect to be able to train a Boltzmann machine, a quantum Boltzmann machine, keeping this in mind. Now, depending on the size of it and depending on the kind of problem. So they're very promising. The reason why they are promising is that, yes, indeed, they are a natural mapping of the optimization problem to the quantum system, because you can imagine that you're going to arrange your system of qubits in such a way that they represent at best your energy function, and then you make it, your training process becomes almost like an evolution. Now, the difficulty there and the disadvantage with respect to a variational approach, the variational approach is almost agnostic in the sense that you can build your quantum circuits the same way you build neural network as a function approximators. While if you want to implement energy function, you need to be able to shape your problem as an Hamiltonian, basically as a problem that you can map on a system of qubits. So there is this physics interpretation that is powerful, but can be limiting.
Thank you. Fair enough. So there are trade-offs, yeah, as I anticipated. Yeah. A quick question from Ronak that I can see. He has asked, how are the quantum operators updated? Is there a gradient style update like the neural network? Or yeah.
Yeah. So do I have it here? Well, I don't say, but basically, yes. So in this loop, what happens is that, so can you see my pointer? If I
Yes. Yeah.
Yes. Okay. Perfect. So this blob here, U d theta, this represents the set of quantum gates. So the operations that are parametric. You can imagine that there is a certain number of theta parameters here. And so what you do is, once you found the updates, so through build the classical loss function optimizer, which is probably Adam or whatever. Once you have your updates, you reload, basically you update your gates, redefining using the new versions of your parameters. And just for you to have an idea, in most cases, or in the simplest cases, those gates are actually, you have your quantum state and you apply rotations. And the parameter typically represents rotations around one of the axes of your basis, and the parameters typically would represent these rotation angles. Okay, this is a very easy way of building parametric systems.
Thank you. I hope this is clear to Ronak. I don't see any other questions at the moment. So as we're running out of time, I'll just have a broader sense on the practical side, because since you joined in 2020 back there over the years, what have been the biggest practical bottlenecks you have found, like while integrating quantum technology into the existing CERN workflow or the infrastructure there?
So for us, to be fair, one of the main bottleneck was expertise building, because we came into this with very little expertise. We built through collaboration with departments. We've hosted PhD students, and through that we were in contact with center of expertise elsewhere. This is not core. This used to be not core business at CERN, but so why am I saying this? Because what you see when people or groups get closer to these topics, and that you see them over and over going through the same tests and making the same experiments, even though for some of those we already know that those are not the right approach, and there is very limited advantage or even interest in actually going this direction. So I think it would be, as a community, it would be very, very important for us to progress much faster, to find a way of sharing this in a way that is more, it's broader. Because otherwise it looks like we are always restarting, all of us in physics, I mean, in the applied technology. I'm not talking about computer science or quantum information people. I'm talking about us as applied researcher. We always restart from the same or from very similar levels.
Right, yeah. Fair enough. As I don't see any further raised hands or questions, so I think things are pretty clear. It was a really nice, interesting talk, Dr. Sofia. Yeah, we thank you again for joining us today. Yeah, so
it was a pleasure.
yes,
Thanks.
exactly. It's a pleasure to have you on board as well. And yeah, we'll be in touch.
Okay,
So,
bye-bye.
yeah, take
Bye.
care. Bye-bye, Sofia.